So the talk I'm going to give is on it's wildfire science using mechanistic models for understanding ecosystems, fire, hydrology, all within the context of climate change and how do we make these systems more resilient. And I'm going to be talking a lot about some mechanistic modeling approaches, tools that we've been developing at Los Alamos, why we've been developing them, and so forth. But first, I should introduce Los Alamos National Lab. It's a really big lab. There's about anywhere from, depending on the year and how you count it, about 12,000 to 18,000 employees. We do all kinds of sciences at Los Alamos National Lab. And we do more than just nuclear science. I'm not sure how many of you have seen Oppenheimer. That's our claim to fame. But we also have an Earth and Environmental Science division that many of you might be interested in. It's where I work, and we do a lot of neat science there. So just a real brief organization of how our division is set up. We're the Earth and Environmental Science division. There's 3 groups. There's the Climate and Ecology and Environment group. I work a lot with those folks, but I'm actually not in that group. I'm in the Energy and Natural Resource Security group. And within that group, there's 4 teams, and I've been shuffled into the Fire Impacts for a Resilient Environment team. In addition to our group, there's a National Security Earth Science group. So you'll see national security is prominently focused on Los Alamos, but it has broad implications, and so we work in a lot of different sciences, including landscape ecology, subsurface flow and transport, earth physics, geological geochemistry, geomechanics, geophysics, explosion monitoring, and then of course fire impacts for resilient ecosystems. And so that acronym actually is FIRE, so that we can remember it. So that's Los Alamos. Really like working there, and maybe some of you might like working there someday too. So a little bit about wildfire science before we start. As you've heard, wildfires are made worse by climate change. Maybe I shouldn't say wipe out ecosystems, but they definitely can transition ecosystems. And they contribute to further climate change. They cause flooding, erosion, water quality issues, smoke and air quality issues. But one thing we shouldn't forget, and this is something that we've had to deal with recently in New Mexico, is that they are displacing communities, and in some instances displacing, devastating lives and livelihoods. And so this is some tragic pictures of the Hermit's Peak Cass Canyon fire, which was the largest fire in New Mexico history. And that fire started as a prescribed fire that got out of control. And so prescribed fire has become a dirty word in New Mexico, and maybe it shouldn't be, but there's a lot we need to do when we are addressing wildland fire science, and particularly prescribed fire, because now we're responsible for the fire that was set. So while only less than 1 in 1,000 prescribed fires escape initial containment, and if you were to flip that on its head at any one given time in the western United States, less than 0.06% of all wildfires at any one time started as a prescribed fire, and only a fraction of those become really catastrophic. But when they do, as we saw last year, it can devastate lives and communities, and so we must do what we can to prevent this. And so there's some relevancy here, and you have to tread lightly. So a little bit about the flow of the talk, so something to expect as we go through all this. I'll first talk about climate change, fire ecology, and the role of prescribed fire. Then I'll talk about some of the tools that we've been working on at Los Alamos National Lab to address some of this, these physics-based wildland fire modeling tools, and then a little bit about the science of fire, water, and ecosystem response to wildland fire and how we model that. Lastly, I'll talk about bringing the science tools that we develop to practitioners. And so that's an additional interesting tidbit about the type of science that we do there. We want to bring basic science into the hands of people that need that, whether it's national security science, or in this case, Wildland Fire Science, and there's a lot of crossover to that. So, as y'all have heard, climate change is making wildland fire much worse. And so these are just two graphs that show that. The first graph on the left just shows increasing acreage from the last, 40 years of wildland fire in the western United States. Now, increased wildland fire area globally is a slightly different and more complex story. I'm not going to touch on that right now, but in North America, we're seeing more and more wildland fire. And as you've probably heard, a lot of this wildland fire can be attributed to climate change. And so this figure from the Abatskalou and Williams 2016, I think, illustrates this, where they tried to separate out burned acreage that is due to conditions amplified by climate change versus those that aren't. And if you notice something, both lines are going up. So wildfires is being made worse by climate change, but there's another thing going on that's driving this that I will touch on. And together it makes it a very flammable situation. So climate change is causing wildland fires to increase in size and intensity, but there's another thing that's going on. Climate change is breaking the empirical models, the empirical based models that almost all the practitioners use to model wildland fire. It's also breaking a lot of the models that scientists are using. And so this paper by Jeff Tollefson, there was a sort of a flashy front page Nature paper, explains that, and it says huge wildfires are defying explanation, so much so that researchers are scrambling to improve our wildland models. And if you have to squint to read this last little bit right here, what it says is so much so that scientists are struggling to model them. So I'm a scientist who models wildland fire. What gives? What's going on? Well, in a nutshell, the wildland fire models that we use to predict wildland fire behavior that is employed by the Forest Service, they're good empirically based models, and it's really good work. I don't want to trash them too much, but the point is that there are these models called Rothamels, Van Wagners, and when you have an empirically based model, basically what that means is that the model is more or less developed on the data that you have. And so here we are, we have all this data, and we can fit a response to that data, and we can adjust and calibrate our model to fit that. But what happens when you're outside of that data range? Those types of models, well, not those types, specifically Rothamels and Van Wagners equations are the basis for almost all the practitioner-used models. I should actually just say all the practitioner-used models, particularly a model like Behave. So if you are watching the news and you see the fire boss doing their news report or their daily briefing, they often run Behave to predict what the fire is going to do that day, and they base their report off of that. Oftentimes, they have to calibrate Behave a lot to get it to do what they say they're going to do. So think about that a little bit. Another model that shows up in a lot of large Earth system models, and man, I guess I am picking on models, but Spitfire also, we use this in science a lot too, especially at the larger global scale models. And maybe we need to be careful about using empirically based models that were developed off of a limited data set to extrapolate globally. So, illustrating that point even further, let's think about this in the context of climate change. If we have the stable past conditions, the reconstructed data from the Mechanistic paper, and the blue line here is the observed NOAA global climate anomaly, so whether it raises or lowers from a stable 0. And the two red lines are our RPC climate projections 4.5 and 8.5. The Van Wagners and Rothamels models, the fire behavior models that we all use and love, were developed right about there. So they're about 50 years old. This year was the Rothamel 50-year birthday. And this is where we are. So we're a little outside of their validation range. And so these models are starting to break down. We're starting to lose our grip on what's going to happen. And of course, we have a lot more to go. So we've been calling this the no analog future. So there's no, how do we model that type of stuff if we don't have that type of condition to observe. Big gear shift here. Now I'm going to talk about the ecosystems that fire happens in. And why is it that even if climate change weren't happening, why are we seeing more fires in at least North America? Well, as it turns out, this paper by Kowarczyk in 2007, I really love their figure where they're mapping out areas around the globe that are affected by fire in some way. And it turns out that about 70% of the terrestrial Earth is affected by fire. Where you don't see fires, the Sahara, just sand, a little bit of the high Tibetan Plateau, and Antarctica. The rest of it, you could have some fires. And as it turns out, and this is a little hand wave, you have to admit, but about half of the terrestrial ecosystems are classified as fire-dependent ecosystems. So we need to chew on that a little bit. Fire-dependent ecosystems. That means that fire, wildland fire, is one of, if not the, defining characteristic of that ecosystem, if we classify it that way. And so what happens when you take fire out of that environment? I like to say it's like taking the water, the rain, out of a rainforest. Do you have that ecosystem? Admittedly, the changes to a fire-dependent ecosystem might happen a lot slower than if you were to drought out the entire rainforest, but there are still changes that happen. Here are three really cool plant trait adaptations to fire that we see in North America. Up on the top, that's what you call a serotinous pine cone. They're in lodgepole, that's a lodgepole pine cone. And a serotinous pine cone means that it needs a certain amount of heat for that pine cone to open up and spread its seeds. So that's a very key fire adaptation. Another one is this thick bark of the ponderosa pine. And that thick bark can withstand heat fluxes around it, and you don't get cambium damage, and you don't ring the tree, and so it can survive a fire that way. And this truffalo-looking tree right here, that's a longleaf pine found in the southeastern United States. And that longleaf pine has one of the coolest life cycles I know of trees. It starts out as a seedling, and it grows up to about ankle high and stays in what we call the grass phase for anywhere from 3 to 10 years. And when it's in the grass phase, it's setting out and growing deeper roots and storing sugars. And then that longleaf pine, that truffula part, when a surface fire does come along, the fuel moisture or the moisture contained in those needles can ward off the fire. Now you get a lot of burning, and you get that stuff comes down, but that apical bud in the middle doesn't die. And then after 10 years, it hits the rocket phase, and it jumps up from grass phase to anywhere between 2, 3, 4, even 5 meters tall, so that it can escape those surface flames that come by. So let's think about these adaptations in forest structure. Forest structure is forest density, where the trees are, their shape, that type of information. I would say there's an adaptation here too that really reflects how these forests work. So if we think about these two forests, we have the ponderosa pine forest on my right, your left. That's what I like to think of as a high frequency, low severity fire forest. So fires happen a lot, but they don't happen hot there. And look at that nice open structure. Back when I was an undergrad at Oregon State, we always called that the park-like ponderosa pine forest. Now let's compare that to the lodgepole pine forest. A lot more dense, a lot more trees in there, a lot more fuel in there. And let's think about their adaptations. Ponderosa pine, thick bark, lots of fire, that's not hot, it can survive. The lodgepole pine, serotinous pine cone, it's looking for a stand replacement fire to reseed that. And that's the kind of fires that you see, generally. Boom. So, structural forest difference, evolutionary traits, I would say they help determine the type of fire behavior that you see, and the ecosystem then responds to that type of fire behavior that happened. What happens when you take the rain out of the rainforest and the fire out of the fire-dependent ecosystem? Well, you get a slow ecosystem transition. You might have the same characters and species hanging out in there. So if we start with this ponderosa pine forest, or at least mixed conifer forest, over time, if you take that fire out, you end up with something that's a lot more dense. There's a lot more trees in there, a lot more fuel in there, and that's a very different fire waiting to happen. In addition to that, when that type of fire happens, is the seed source the same as a lodgepole pine forest? Is it going to reseed the same way if they're not serotinous pine cones? Those are things to think about. And so that's one of the reasons why we're getting ecosystem transition. So to sum that up again, effects of fire suppression, you can have your fire frequent forest right there. If you have low intensity fire, you likely get ecosystem stabilization, so it's not going to transition, it's maintaining its fire dependent state. If you don't, you get gradual ecosystem transition, and this is that proverbial tinderbox you hear people talk about. And when a fire comes through, you look like this, and this is a picture taken out of after the Los Conchas fire in 2011 that threatened to burn into the Los Alamos National Lab. In addition, fire-dependent landscapes do store carbon. This paper is a figure from Polly Barrett's paper. I really love this paper. And what they actually set out to do was to classify what forest should we be protecting, or what forest should we prioritize in terms of carbon storage. And of course, they love the wet forest of the Northwest as its carbon priority rank. But I would argue, what about all that other area that makes up about 80% of the forest we see in the West? Turns out, collectively, that area stores more carbon than that small area, even though it's less per acre. And that forest tends to be very fire dependent, more drought stressed and more fire stressed, as it were. Nonetheless, it can store, I don't know, back of the envelope calculations, I was coming up with 21 years of current regional fossil fuel emissions. So maybe a decent climate mitigation strategy to also focus on those forests as well. And I tend to live in those forests. So how might we do that? Well, this is where the dirty word comes into play. Prescribed fire in action. Why do we intentionally let the landscape on fire? Why are we trying to create low severity fire? Well, we're trying to knock back that high severity fire coming along. And so this picture is a really nice illustration of prescribed fire in action. You can see the different treatments labeled here. Thinning only, didn't quite do the job. Did a heck of a lot better where there was no treatment. That looks pretty scorched. And then the thinning and prescribed fire, that's the kind of forest we want to see when a wildfire moves through. This particular wildfire was the Bootleg Fire in south central Oregon. And one of the really cool things about this fire, or actually not this fire, but this prescribed fire that happened, was that it was in coordination and led by the Klamath tribes of southern Oregon. And it's a great illustration of how indigenous management practices, needs, cultural practices have a lot to teach us about forest management, particularly about indigenous burning practices, which I'm learning is not just a North American thing. I was talking to a colleague of mine from India, and she was pointing out that there's a lot of indigenous burning practices there as well. So at this moment, I'd like to take just a minute to really let that set in. We have these peoples that have been here for a long, long time. And I really love this really cool discovery from last year, 2 years ago in White Sands, New Mexico, where they found these footprints that they've dated between 23 and 21,000 years ago, which sets peoples here well into the last ice age. And so they've been out leaving their mark on the landscape in a lot of different ways. And one of the ways that they leave their mark in the landscape shows up in the forests that we see. So when the white European foresters came out and forested out here, they came across these, again, park-like ponderosa pine stands that had this open understory. I would argue, as would some of my friends in the Yurok tribe and the Klamath tribes and the Pueblos, that's a managed landscape. It's not necessarily devoid of people's hands. And there was a lot of indigenous burning practices going on. Other benefits to prescribed fire. Does it work? Prescribed fire equals wildfire reduction. Here, or in the southeast, where we have that truffula tree, lodgepole pine forest, they've been doing a lot of prescribed fire there. In fact, that's where you have most of the prescribed fire in the United States. Happens in the southeast and on Department of Defense lands. And this is Fort Stewart. The yellow bars are acreage burned after they started their prescribed fire burning regimes. The green line, that's this red cockaded woodpecker. It's a species of concern that they need to take care of. It's a fire adapted species, loves the prescribed fire stands. And then the red line, that's the unintended wildfires. And so you're seeing that nice trend pull out or shape up and form. So I think maybe I've convinced you that prescribed fire is at least a tool to consider. What's the deal? Why is it dangerous? Why do we have problems with it? And how do we use it? Well, obviously the idea is we want to take a landscape that is fire suppressed. So we've done a good job of taking fire out of the environment. We're having trouble keeping it out. As a result, we are not dealing with a landscape that is well suited for fire, but sorely needs it. Without prescribed fire or some sort of fuel management action, there's a high risk of ecosystem transition. So we want to go this way, a science-driven prescribed fire framework. The trouble is that wildfire science to date has really focused on the high severity wildland fires. And the high severity wildland fires, everything's dry, it's going to burn. If it's doing that, run, get out of the way. It's really, really hard to stop. That same science doesn't really address prescribed fire conditions. What's the difference? High severity fire happens when everything's a tinderbox, it's going to burn, and it's going to all burn. Prescribed fire, we're talking about moderate conditions that are in fluctuation. And so in those conditions, things like forest structure, fuel moisture, all those things have a bigger control on that fire behavior. And those things can change rapidly too. And so because they can change rapidly, we need modeling tools and knowledge that addresses those fine scale problems that have big scale implications. So we need a new fire science strategy, a prescribed fire science basis. So now at Los Alamos, what are we using to address this? How do we address the problem of climate change breaking our models, which is a really hard problem? How do we capture all that fine scale stuff? What are we going to do that? One possible solution, not the solution, one possible solution is to base your models, instead of off of empirically based models, more physics-based, more based on mechanistic interactions. And so this particular model is called FireTech. It solves the Navier-Stokes equation in the atmosphere. So it's really solving what we think of as the turbulence and the eddy formulation and the drag of the forest. We represent the trees as 3D trees because that's what they are in space, and that's what the wind sees, and that's what is moving fire from one place to another. And we try to, as much as possible, solve all the energy balance and conservation of mass and momentum equations needed to get at combustion and wind-driven fire. And so then you can take a tool like this and you can say, well, what happens when we run a prescribed fire in this particular hill slope. And so maybe it's bounded by these roads. Maybe we can see where the fire is more intense. Maybe we can see, is it meeting management targets, clearing out the fuel? Is it staying out of the canopy, underneath the canopy? And is it getting escaped? In this particular simulation, we can see you might want to reinforce that area right there because it got out, and you don't want that to happen. So as an example. All right, mechanistic approaches and what you get. And I should have titled this Mechanistic Approach to Fire Effects, or how does the forest respond to fire itself. We're going to take these models and look at something called crown scorch. What crown scorch is just you've cooked the tree to a lethal temperature. You didn't burn it, you just cooked it. And it kills the tissue. And it's one of the, outside of burning the whole tree down, it's one of the biggest fire effects to the forest and has one of the biggest implications in terms of landscape ecology. So we're trying to use our 3D simulations to identify resilient forest structures to crown scorch. We're trying to see, can we get this type of model to work? And then what does it mean when you start to look at 3D forest structures? So yes, indeed, we can get it to fit the data that we have. In fact, we might as well use the empirical data used to create the Van Wagner model to see if our model fits it. Does a decent job. We're maybe a little low here, but by the way, these little X's, that's actual data that Van Wagner used to create his nice model right here. And then the blue is our model, and we get a whole lot more variation because we're resolving a lot more. We're getting all this turbulent fluxes and buoyant plume dynamics and different heating profiles because of how the fire is drawing in wind and sucking the fire or the heat up and cooking the canopy in different ways. But point is, not bad for not having to calibrate. What happens when we change the forest structure? So now let's think about our lodgepole pine forest versus our ponderosa pine forest. Let's simulate them and see how much of the canopy do we scorch in the lodgepole pine forest versus the ponderosa pine forest. And as you can see, our dense trees, this guy here, we get a lot more crown scorch, especially as we increase the intensity of the fire versus the more open canopy. And I'll talk a little bit more about this later, but it's because of the increased convective cooling that you get with a more open canopy. It just sort of naturally bleeds off the heat a little bit better. Another nice experiment we can do with this tool is we can think about, well, what about forest structure and its heterogeneity across the landscape? Does that affect fire behavior? Most, if not all, models used by practitioners don't resolve 3D forest structure. In fact, they just resolve an even density forest across the landscape. What are we getting with all this? Well, we can start to look at forest structure variance. Where is the fuel dense? Where is it not? What are the correlation links between that density? So how far do you have to move along the ground before you're moved from a real dense batch of trees across the clearing into another dense patch or into the clearing itself? And we can kind of randomize it, and so we can get more characteristic behavior and run a bunch of simulations. Kind of hypnotic there. Those are all of our different domains. And then we can have a result. We can say, oh, well, now we know that fires move faster when there's clearings in the forest. So if you put these big clearings in the forest, you get what we call wind entrainment. That's what we're trying to show here. This is vertical wind speeds in the canopy, and you can see you might have a clearing here that speeds up, and overall you get more wind speeds in the canopy to drive the fire forward. So its rate of spread is a lot faster. We can look at a forest that looks a lot like a plantation, where all the trees are the same size. They're not taller, they're not littler, they're not spaced out differently. Turns out, because everything's smooth, that wind can blow through that canopy, or at least above and below it, rather fast. And there's continuity in the fuel, so the fire burns much faster. And that's that guy right there. And in this particular simulation, albeit low wind speeds and decent fuel moisture. Our wild forest that had canopy gaps and branches sticking up and down, it tripped up the wind. It's like looking at rocks in the river and creating all these little eddies, and the fuel was discontinuous. And it was really hard to propagate the fire in that type of environment. It doesn't happen in all wildfires. In fact, when it's, again, super dry, super windy, it's going to burn. But in a prescribed fire setting, you might want to know that. So what else are we doing? We're trying to figure out how the ecosystem itself is responding to the fire. So this is a modeling framework that we've put together. I call it the disturbance and ecosystem response model, or disturbance and response, so it's like a call and response, where we take our fire behavior models, quick fire, fire tech, that resolve the 3D forest structure. We burn them, map the injuries onto the trees, feed that into a hydrologic model, and a plant successional or ecosystem demography or ecosystem process model that then can build up the fuel for the next fire. So now you can start to look at multiple prescribed fire return intervals. You can look at how does different intensity of fires affect the ecosystem, or at least that's the goal. And so we can take things like, oh, well, we know in this section of the model, trees are really dense, not so dense, halfway dense. We can then estimate where those trees are, plot them in the ground, play with things like randomize that, or try to come up with analogs to what we're seeing out there. Same thing with surface fuels. That's a bit more straightforward, as it turns out. We know underneath trees there's not a lot of grass, but there's a lot of litter. In openings there's a lot of grass. Maybe the ecosystem demography model told us this. And then we can create the surface fuel distribution and run our fires on that. And then, taking into account crown scorch, we can cook the trees, we can burn the trees, we can get an estimate of which trees live and die, and where they live and die, and how those holes open up. We can take a look at different prescribed fire return intervals and see what type of forest structure we're getting with these ecosystem demography models. And so here we just tested a 6-year fire return interval on a longleaf pine forest versus a 3-year fire return interval. And we can see that there's characteristic forest structures that develop based on these fire return intervals. And if you remember our ponderosa versus lodgepole pine comparison, it's pretty obvious what each one of these looks like. We're getting a very different, more open forest structure, more closed forest structure, and so forth. Another thing, and I'm going to try and take you step by step through this one, we can look at how prescribed fire or a fire might change the resiliency of the forest to fire by changing the 3D forest structure of the canopy. So if we start off with what we consider a fire excluded forest, and I should mention, if you haven't noticed already, each of these blue dots represents a tree on the landscape. So lots of trees. We introduce a fire, and there's some details I'd like to point out on this one. You can't see it here. Well, you can if you pay close attention. We put in 3 different fire lines. We started there, we started one there, we started another one there, and then we let the fires burn across the domain and interact. So, and this is a plot of fire intensity, so kind of wherever it's red, it got really hot on the surface. And we can see that, this was a moderate fire, but it turned out it killed a lot of trees. Didn't kill quite as many over here. We had multiple fire starts. Killed more over here where the fire got up into the canopy and ran and had a longer fetch. I think fetch is the right word there. And then we can grow our ecosystem over again. Say, let's run that model for 5 more years, 10 more years, reconstruct the surface fuels, and then run another fire. This fire, we made more intense. We just took out moisture in the surface and changed things that way. And here, it's much easier to see those 3 fire line starts. 1, 2, 3. And that surface fuel burned a lot hotter, got a lot more intense, a lot more energy, but it didn't kill as many trees. And that was very interesting. We tried to figure out why. And what I think is the difference here is if we look closely at the convective heat transfer, and I'm going to just take you to the slide that investigates that. So joules per second on the y-axis, time of the fire, and we have fire 1 versus fire 2. The two blue lines are the first fire, the two red lines are the second fire, and we separated out surface fire convective heat transfer in the second fire versus the convective heat of the surface, and the convective heat transfer in the canopy. And so along the surface, we can see, yeah, we did indeed cook it a lot more intense surface fire. So dark blue line to dark red line. Slightly but effective increase in convective cooling. And I say increase in convective cooling, but it was a decrease in the heat transfer to the solids. That's how that showed up. That looks to be one of the reasons why we're seeing less tree mortality. So we're not able to cook the canopy as much. We're not able to get as much crown scorch. In fact, I saw almost no crown scorch. And we're not able to make a canopy run. Also, there's less trees to burn. Shifting gears once more, a little bit about fuel moisture. We can try and model this fuel moisture here. And so here we're thinking about fuel moisture, how it changes fire behavior. There's two different types of fuel moisture. There's live fuel moisture. That's the moisture within the plants. That's a plant trait, ecosystem trait. Responds to climatic drivers, soil water stores, versus dead fuel moisture. That's what's held on top of the canopy or in the dead material. That's a little bit more rapid response, and it's determined by weather and vegetation structure. Vegetation structure probably affects live fuel moisture too, but we haven't gotten that far. Oh hey, there's that guy. So one of the works that Caleb did for me over the past couple of years when he was at Los Alamos was he took this power flow model and overlapped our 3D forest structure from FireTech, and then implemented this plant physiological model called EcoSuros, and soon to be Fetch, to look at what is the plant physiological response to the soil moisture that we're seeing over time. And if we have, say, lateral groundwater flow, where you have a hill slope and a stream boundary condition, do we capture wetter live fuel moisture down here, drier fuel moisture up here? Indeed we do, and it does affect fire behavior. I took that slide out, sorry. Can we look at dead fuel moisture evolving over time? So what about the 3D forest structure? Here we have a ray tracing algorithm that basically casts shade on all of the fuel structures. We consider that the entire tree and all the surface fuels. And we could march that across, we can evolve that over time and see how does it dry out as the sun arcs across the sky, and it dries out as you would expect, not underneath the trees, more in the opens, in the clearings faster. We can think about what are the fire effects to hydrology or water balances across the hill slopes. And so if you think about fire suppression, what it's done to these forests is it's created forests that were open, a lot fewer trees to forests that are more dense. You might get a lot more evapotranspiration because you've increased the density of trees in the landscape. You get more interception. So if you think about your water balance, you have precipitation being intercepted by trees, transpiration, infiltration. If you have a lot of trees, a lot more interception, more T, less E, maybe less infiltration. So there's an effect there. So can we use our models to get at that? This was a study we did several years ago now, where we just simulated water balances at site scales in the Las Conchas fire, which happened in 2011. The study happened in 2018, 17. And then we simulated, we gathered data, forest structure data from surveys that Bandelier National Monument put together. And we had low severity sites, moderate severity, high severity sites, and then just look at the water balance. And as we see, as I just explained, if you are taking trees off of the environment, you might get an increase in the water balance. And so here in the low to moderate severity fire, we took some vegetation out. We indeed saw less transpiration and an increase in soil water storage. It didn't hold at the high severity sites because we saw a lot more runoff. This was due to hydrophobic soils, things like that. We also saw a lot more bare soil evaporation. So if you take off all the trees in some environments, you actually could get less water under certain circumstances. And then one of the projects that Chuck and I am working on, this guy right here, is that guy right there. Another UT Austin alumni, by the way, is we're trying to think about, can you optimize 3D forest structures for watershed yield? What type of information do we need? Can we characterize forest structures broadly across the landscapes? And so Chuck has been working on high resolution satellite imagery and terrestrial LiDAR to understand tree height, tree density, crown radius, and he's doing a really good job of it too, as is expected. And does, you know, we haven't got to it yet, but we wonder, one of our hypotheses is, do we see certain forest structure types in productive watersheds? Is that something that we see? I just had a good conversation with Daniela today, and she was saying, you know, there's a lot on the fire disturbance literature out there, but it's very inconclusive. And we'd like to see, if we look at this as a big data, kind of a larger scale approach, do we see something a little bit more conclusive with the, and by the way, I have no idea how much time I have left. I didn't track my time. The general idea here is we want to optimize landscapes and landscape services or ecosystem services through forest structure, because that's one of the things that we're getting at when we're re-implementing prescribed fire. And we want to optimize for things like terrestrial carbon stabilization, water resources, and of course, wildfire risk. Now, just talking briefly about how are we getting these tools into the hands of practitioners. Everything I showed you right now requires a lot of computational resources. And that's what we have in Los Alamos. We have a lot of computational resources. So fire tech requires HPC, and to resolve that type of model, it takes a while. And it's not something that your forest practitioner management has at their fingertips. And they are resource starved, as is a lot of people in the BLM Forest Service. What can we do to help them out? And so we're collaborating with UC San Diego and ILCAI on this Wildfire Commons to build up platforms that provide access to fuels data, 3D forest structure fuels data, and we've constructed a faster running proxy model that practitioners can use on a laptop called QuickFire. And so here, this allows, we're hoping it allows land managers to prioritize land that needs to be burned or is dangerous, gives them an idea for burn planning. They can run scenarios out on the computer with the fuels that they have and see, you know, what's dangerous, what's not. And oftentimes they need to actually have the people power to implement the prescribed fire is one of the biggest limitations. So some quick examples. See Chuck's work's getting there again. He's using that same framework to characterize fuel. We're partnering with the Forest Service on a project that they call Fast Fuels, that allows them to create synthetic landscapes or representations of what we think is out there. So the closer that representation is, the better that fire manager can identify locations that need burned or don't need burned. And then we can use this model called QuickFire that runs a lot faster than fire tech, and you can still get that 3D forest representation. We're still capturing some of the wind conditions, not quite as detailed as fire tech, and we get information about fire intensity, fuel moisture and effectiveness of the fire. And so with that, I'm going to wrap this up here pretty soon. But before I did, I wanted to talk a little bit about the landscape that we are in at Los Alamos National Lab, the types of fire we've had, and in context with the types of fire we're seeing around the world these days. So since 2020, we've had several large fires. We've had the Cerro Grande fire, another escaped prescribed fire, that burnt into the town of Los Alamos, and people lost a lot of their homes. I wasn't around for that one. By the way, that's where Los Alamos is in this map. Then we had the Lost Conscious fire in 2011 that added all of this, and we were starting to see fire behavior we hadn't seen before ever. The fire was exploding overnight. That's not something usual, and it's not something our models predicted. Jury's still out on what's caused that. We had the Thompson Ridge fire. I didn't even name that one. And that was right here. And then we had the Cerro Pelado fire just last year, and we were almost had to evacuate again. And that was a fire that burned here back across the Lost Conscious fire. And so we're seeing this fire behavior. We're starting to see bigger and bigger fires, and some places are sort of a bellwether for what's coming for other places. And we're starting to see these fires happen. Well, we've always seen them happen in California, but we're starting to see them happen in Oregon and Washington. This year was Alberta. But just because the landscape is getting routinely torched, and I say we're losing ecosystems, there's still stuff there, and it's still stuff worth preserving, worth checking out. And it's a landscape that's pretty darn resilient. We're getting ecosystem transition, but the ecosystems are fighting hard to stay put, to stay where they are. And so here's some pictures of some aspen regeneration. That's my son right there. This is, by the way, this is downtown Los Alamos. Looks not at all like a city. My house is right over in there somewhere. But it's a fire-affected landscape. These hills are, it's just a pretty picture, but these hills are completely burned. They used to be green and now they're not, but they're starting to grow back aspen region. This is the Pajarito, the little ski hill behind our town. Beautiful aspens right now. And we're seeing the trees that survived the fires survive the next fires. And, you know, so the trees that survived the Lost Conscious fire are doing quite well after the Cerro Pelado fire. And these trees are coming back. And as I hike around and get out there, I see seedlings in places I don't expect to see them. I see them dying too, but you know, it's just an amazing landscape, as you can see. And one of the things that I really enjoy about this type of work in a place like Los Alamos is that I can get up from my computer after working on this and I can walk outside and see the forest that I'm trying to work on. And it's a really cool part of the job, and it reminds me that it's important to put it in context of what we're trying to do. And with that, I'd like to quote this quote from a old trusty conservationist, and he says you should also get up and get out. And as he puts it, he says you should save part of yourself and your life for pleasure and adventure, and get up off of the computer and look at that landscape. It's not enough to fight for it, or in our case, just study it. You need to get out there and enjoy it while you can, while it's still there. You need to get out and hunt and fish and mess around with your friends and ramble about yonder and explore the forest, climb the mountains, bag the peaks, run the rivers, and breathe deep that sweet, lucid air and sit quietly a while and contemplate the precious stillness, the lovely, mysterious, fire-affected landscapes and awesome spaces. And if you do that, I love this part, I promise you this, that you will have this one sweet victory over our enemies, over those folks, those men and women with their hearts in a safe deposit box and their eyes hypnotized by their desk calculators. I promise you, you'll outlive the bastards. So with that, we'll take questions.